sad and then. All right, that seems promising. All right, I'll move this over here. Everyone can see that? Fabulous. Okay, so I am the only one you have today because Vonica and Michael are out and our guest fell through. So it has fallen to me to put together something very last minute so that we have something to talk through today and keep the seminar running. And so what I have decided to do is to put together some notes on AI hardware. Hardware is something that is increasingly important and variable in our field, especially relative to how it was in previous decades, where computer scientists could really focus on the software part of it. And nowadays we really have to care about more of it. The software is it's frankly not so complicated anymore compared to what it used to be. It's all very simple and parallel, and really the hardware is a big part of what's driving it. And yet I feel that the pedagogy has not necessarily updated to reflect this new reality about how computer science is done. And we still spend most of our time talking through various algorithms that were designed for old CPUs that are actually fairly unrepresentative of what modern hardware looks like. So for today's class, I thought I would put together some notes on AI hardware. It will partially be a dissection of an H100 in terms of both what the H100 is and also the manufacturing behind it, because I think these are things that are worth knowing. But I'm not going to go into like extremely high depth on H100s either, unless you were planning to write CUDA. The set of slides that I have is scoped out probably to run 45 minutes or something like that, if that. So all this is to say that I'm happy to end a little bit early today, but this is mostly designed for like ask lots of questions. This is a blank canvas for you to find what you want. I do not guarantee I'll have answers to all of them, but I may have answers to many of them. And I think it is a nice chance to get a window into a part of the field that most of us don't actually spend that much time engaging with. So a bit about what this presentation will be. We will start with why, and I will summarize again why I think this is so important. Then we talk about what the AI hardware sort of is today, and then we will go to how in terms of how it comes. So let's start with why. For AI, compute seems pretty important. If we look at the scaling of AI systems over time, what we see is that we all know this, that the amount of compute has exploded quite dramatically. But I might go so far as to say that actually most of what our field has accomplished in the last 10 years has actually been given to us, or well, we should say we bought it from Jensen Huang in terms of improved compute. That the architectures that we have today are a little bit more advanced than we had in 2017, but like not that much. We're still running on pretty similar stuff to we ran 5 or 6 years ago, and to the extent that the stuff has gotten better since then, this is the bitter lesson, right? It's come mostly from our ability to better leverage massive amounts of computing data. And it's not because we've gotten that much smarter, we haven't gotten that much smarter. I don't mean to entirely discount the work of the field of algorithmicians. I think that would be an unfair extreme characterization to go to, and obviously the architectures we have are much, much better, and our understanding is much better than it was 10 years ago. But in terms of what has really driven the pace over the last 10 years, I wish I could look back and say that it was driven by us getting so much smarter and figuring out how to do things with little bits of compute here and there, but that's not really the story. The real story is that the chips have gotten a hell of a lot faster, and we've just figured out how to keep up with that and continue scaling with the compute and data. Now, of course, why else should we understand the hardware? Well, understanding the hardware does help understand our limits in terms of what we can and can't do and where things are going. As you've all probably seen, the performance of GPUs has gone up quite tremendously in the last decade, about 1,000x. The breakdown of exactly what causes this 1,000x is also fairly interesting. Interestingly, the largest driving factors actually reduced numerical precision, which was responsible, according to Bill Daly, for about 16x of that 1,000x. There's a bunch of other things, specialized hardware in the form of tensor cores and whatnot that improve it. Continued improvements just from like regular process scaling drives part of it. But the biggest factor actually is being able to tolerate lower numerical precision, which is an interesting side fact. And I mean, the pace is just ridiculous, right? That we used to have in 2012 when the AlexNet networks were trained, we were running on maybe a couple of teraflops per chip. You probably weren't even really realizing all of that because we weren't as good at writing fast kernels. And nowadays we're running on thousands of teraflops per chip. It's just an insane amount of compute that we have. What chips can do in a couple of milliseconds. Yes, go for it.
Could you
Oh, well, so the if you go back to, let's say, the K20, I think this is actually visible a little bit here, right? Everything is being done in floating point 32 FMA. So FMAs at least were a thing back then, so we did have fusion of those operations. But when you're running in 32 bits, the basic challenge is that so floating points are fairly annoying to do addition on. The multiplication is actually not that bad because you basically just add up the exponents. You do have to multiply the mantissa, but what makes the floating point addition quite irritating compared to like a normal integer addition is you have to basically do a bunch of these barrel shifts to align all of the mantissas according to the different exponents of it. Then you do your sum, and then you sort of have to go and realign everything back and decide where it was. And what has essentially happened is that we have updated our algorithms to realize, hey, we actually don't need the full precision of a 23-bit mantissa. We can get away with like a 7-bit mantissa if you're running in BF16, or if you're running in FP16, then you're using a little bit more mantissa, a little bit less exponent, but it's roughly the same story. And so as the precision gets much smaller, the number of transistors that you need in order to run a multiply or an add also decreases actually even more dramatically. And so then you can pack a lot more multiplies and adds on a chip. And it's not just about the area, as we'll see in a second, it's also really about power consumption. Well, my slides aren't really equipped to sort of talk about power consumption in that much detail. I have like one little piece of it that I threw together. But a big part of what is throttling performance on modern chips is our ability to get rid of the heat and to drive enough power to them. The electricity is not really an important OpEx cost, as we'll talk about later. So it's not really driving the economics of it in the sense that like we need more power efficient chips to save money, but it is an issue in the sense that being able to control power and remove power on a chip is it's a real problem. So when you're able to reduce the amount of power consumption in a particular floating point operation, you can get much more in the way of these operations. I mean, to what degree you can quantize, I think, is still a question. This is actually an area that I am like researching right now. I'm very interested in going to even higher levels of quantization when you're doing training. So I think we don't entirely know what the limits of it are. I think that there's a fairly good chance that we're starting to get close to like sort of full information theoretic usage of the bits. That is to say that like you might have this intuitive understanding that as a floating point number gets really, really long, those like bits way out in the depth of the mantissa are not, like they're not containing as relevant information as the stuff before. So the kind of fraction of the usable information goes down as it gets longer. But maybe you don't have to go all the way down to 1 bit in order to get a pretty good fraction. Maybe you're getting 85% utilization even when you're at 6-bit precision or something like that. And so there's some trade-offs here that are interesting to explore. But I digress. We're still in the Y phase, but hopefully, does that answer your question? Yeah. Okay, fabulous. Anything else? Okay, cool. So yeah, so the chips are getting a lot faster. There's additional tricks that we're continuing to play with them. There may be further additional tricks to play. One of the reasons why I wanted to give this particular talk is that I'm trying to get the folks from Etched.ai. They're a startup that are building transformer-specific hardware to come in a couple of weeks to months. And so I want, they'll probably talk a little bit more detail about it, but this is also meant to be a primer so that, we can understand what they're doing a little bit better when the time comes. So why else do we want to understand this? Well, we need to understand hardware in order to YOLO our Nvidia calls much better, right? That the options trading is, depends on understanding hardware well. So that's, of course, important, and the stocks do reflect this. This was taken last night, and Nvidia is closely catching up to Google, I think, in overall market cap now. So there are real consequences to the economics of this, and that's why at the end of my slides, I'm going to talk a little bit about the economics of these chips and what's driving it at the moment. There's some interesting stuff there. Okay, so let's talk a little bit about what. So this is an H100. I think they've probably stylized the die of it a little bit in order to emphasize the colors, but actually you can see quite a lot about the chip here. So I thought even before we go into talking through the sort of microarchitecture and getting down to the nitty-gritty, it might actually be worth like pointing out what is actually going on this chip. So most of what's important is happening in this area, right up there. And that is the logic die, which has the 86 billion transistors that make up, the majority of the work of the chip. That's what's doing all the compute. So you can actually see, so these little tiny yellow squares are the actual SMs, the streaming multiprocessors that exist on the H100. And so if you actually count them up, you'll see that it's the top is 6, the bottom is 6 rows, and then it's 3, 3, 3, 3. So there's actually 144 SMs that are created on the chip. Now, Nvidia actually doesn't enable all of them. I believe they enable, I'm going to say 132 on the SXM version of the chip, and they enable like 114, 118 on the PCIe version of it. The reason they're doing this has to do with something called binning. So basically, on these modern process nodes, you can't actually guarantee that every single transistor gets made correctly. So what Nvidia is basically doing is they're making sure that they can tolerate failures in some of the SMs during testing and just disable them. And that way they can get their much higher yield. So Nvidia, I believe, is reportedly getting something like 90% parametric yields on their 4N process node that you're using with TSMC, which is actually quite good. It's also necessary because they're using such a large chip. This chip is about 814 square millimeters, which is very close to the maximum size you can actually produce on modern fabs, the maximum size being 830 square millimeters. That has to do with the limiting factor of something called the reticle, which we'll talk a little bit about later. This is one of the kind of limiting steps in how the chip is actually made. But when you have such a large chip with so many transistors on it, the probability that some of them are wrong goes up. And that's why you need to have some sort of tolerance to be able to disable parts of the chips without scrapping the whole chip. And that's essentially why NVIDIA is only shipping 132 active SMs, even when they have 144 that's on it. You can see different strategies in different chips that different companies make. So for example, Google's TPU 5e, I think it's the 5e, which is their most recent inference chip, is actually much smaller. And the reason that it's so much smaller is that it doesn't have the same kind of highly multi-core architecture to it that enables them to disable individual parts of it. So if they made it really big, they would kill their yields. So they have to use this much smaller chip and then solve networking separately. We'll talk a little bit more about that later. The next thing that you can actually see on this is you can see the 4 little chunks of L2. So this is the actual cache. The H100 has about 50 megabytes of L2, as we'll see. So this is kind of the relatively low level, not the lowest level, but relatively low level memory on the chip, so that you don't have to go to HBM quite as often if you're dealing with sort of moderate sized objects. The next thing you can see here, you can actually see the memory controllers. So these are 2, 2, 2, and so on for each one. NVIDIA only actually ships with 5 stacks of HBM on this, so it's 5 by 16 as opposed to 6 by 16. You can see that there's 6 memory controllers, but they actually only enable 5 of them on an H100. Then you can actually see the HBM stacks that are packaged right on the chip next to it, so they're very tightly integrated in order to get that full bandwidth between them. And then everything else on the chip is actually just power supply, basically. So these little kind of flat chips are the power stages that convert step down from about 12 volts to 1 volt. These big blocks are inductors to smooth out the currents. These are also, those are capacitors to also smooth out the currents. And then you can actually see as well, this is a 48 volt to 12 volt step down on the chip. And that is basically, since you're putting these in sort of big racks and data centers, you want to be driving them at relatively high voltage as possible, so you can use somewhat thinner wires. So NVIDIA enables you to run them at 48 volts for that purpose. The actual data center power supplies are much higher than that, but they get stepped down separately to 48 volts, and that's what the H100 takes in. Any questions on this part of like what an H100 is? No, cool, okay. I just think it's kind of fun to actually go, like, you'd be surprised how much you can see just like looking at the picture that NVIDIA gives you of what's going on inside the chip. But I mean, NVIDIA is not hiding any of this. They actually do give you a much clearer diagram of all of the different parts of it. Excuse me. So again, we have lots of little SMs here. These are the things that do all the work of it. You can see the L2 broken down into the 2 main sections of it. You can see the 2 by 6 sort of memory controllers for the HBM3 that's on it. I guess I didn't talk about the PCI or NVLink connections as well. Yes, question?
I was going to ask, so it looks like each SM is linked to one of 5 or 6 HBMs, right, memory banks. So how do streaming multiprocessors access HBM from other banks? Are there like levels of?
Yeah, so this is a great question, and this is something that NVIDIA does not tell us because there's certainly, so it is true that if you, depending on which SM you are, your actual latency to HBM will be a little bit different based on which HBM you're proximate to. I mean, NVIDIA certainly has other circuitry that's going on in here in order to enable you, like, this SM to go get HBM from over there. So it's not like it's completely partitioned. There definitely are going to be links between these to do it, but there are differences. So you're actually kind of right to call that out and say, hey, there's differences between these things, because on older architectures, you generally got that stuff tried to get masked by NVIDIA, and this was true of other manufacturers, that you sort of, when you have a CPU, you want to think that all of your DRAM is like the same, and you don't want to like be, partitioning between which ones are important. But as we're going for more and more performance, when you try to mask those things, you pay some performance overhead somewhere, right, that's going on. So Nvidia has sort of stopped masking a bunch of that stuff and is now putting the burden on the programmer to really figure out how do you actually do this well. They're not doing a great job of it, in my view, because they're not making it super clear that like you need to do these things. You have to go and like run your own micro benchmarks to see what's going on with it. But yeah, that's a great thing to point out, and that is absolutely true that these are like real physical devices that are subject to the laws of physics, and so as much as we wish that we could abstract and say everything's at the same level, everything's this, like sometimes that's true when the hardware designers are nice to us and they give us those properties, but we don't get those properties for free. We pay something when we get those properties, and the hardware designers also sometimes choose not to give us those properties. Does that make sense? Cool. So let's actually go and look even a little bit in more detail, and this is again just NVIDIA's docs of what they tell us is going on in it. So we're now zoomed into kind of a single SM, and what you basically see that we have here. So we have, first of all, we're going to ignore the texture stuff. We have a 256 kilobyte L1 / shared memory. So the L1, this memory can be reconfigured by the programmer to either serve as an L1 cache if you don't need that much shared memory, or you can have shared memory to share among different thread blocks and basically enable you, or different warps, and enable you to have kind of a very tight level of communication within the SM. Then you have, also there's an instruction cache at the top. We're going to not focus too much on the instruction pipelining. Within each individual one, there's a bunch of circuitry involved in the loads and stores and moving the memory around. Then we have a bunch of parallel units to do integer computations, floating point computations, even double precision, which we're not really going to care that much about. The most important thing here probably is the tensor core, which is driving the vast majority of the performance of the chip. It's specifically, if you are not using tensor cores, you're paying about 30x in terms of overall performance that the chip is able to drive. I will show you what particularly architecturally enables that in a moment, about how a tensor core actually works at the lowest level. And this will extend to all kinds of matrix multiply units. And then we also have some additional things in the focus. We have the warp scheduler that's actually going to basically go and say these are the bits of hardware that are going to actually execute these bits of code. We have the register file, which is going to have the kind of very fastest available memory to be running things with. L0 instruction cache, other things like that. So there's a bunch of things I want you to notice from it. So first, this thing is engineered for just mountains of bandwidth. Everything is highly parallel in every possible way. And we see this both from the top levels of the HBM all the way down to here, that everything is the widest bus it can be to do as many things as possible at once. We'll notice that there's actually a fairly deep memory hierarchy here, and this is something I actually want to call out as both one of the benefits of the way that modern GPUs are designed, and also kind of one of the drawbacks. Deep memory hierarchies make fundamental physical sense, right? That when you have locality in terms of data on the GPU or on any sort of silicon, and so when data is really close by, you can get it more quickly. But of course, the downside is there's only so much space that's really close by, and unless you're going into 3D, which has its own host of problems, right? That's like very tightly constrained. So you have to find ways to go further away. But now, of course, that's going to get more expensive. So you want to kind of create this hierarchy where you say the things that are close I can get really quickly, and I'm going to create their own special box for those things, and the things that are a bit further, and so on and so forth. So this is the way to do things efficiently. The downside of it is that, in my view, most of where the inefficiencies in terms of low utilizations come from basically actually stems from bad utilization of the memory hierarchy. That actually laying things out well and using the memory hierarchy really efficiently is like the key hard thing to do when programming GPUs to be really fast. So if we take something like flash attention, which True was talking about last week, most of what flash attention is it's this like fairly clever set of tricks that you need to do in order to keep things as low in the memory hierarchy for as long as possible, do all your computation there, and do as little writing up and down that stack. And so what you basically find is that if you're not careful and you're constantly writing back and forth from the wrong layers of the memory hierarchy, you're going to screw yourself, and you're going to get really bad utilizations because you're basically bottlenecking yourself on that memory bandwidth, and everything's stalled all the time. Whereas if you're actually able to use the memory hierarchy to its fullest extent, then you're going to get basically the max performance that you can get from it. And so this is something I kind of want to call out as something to just like, if you're building a mental framework of how hardware works, like the memory hierarchy is really important in terms of what it kind of dominates the overall dynamics of how you program it efficiently. And there's not really a way around it at the moment because it has sort of physical parts to it. But at the same time, if you don't respect it, like it will punish you. We, of course, also have tensor cores. And so, as I said, this is a huge factor in terms of what makes these things so efficient. The area of a tensor core on an H100 is actually surprisingly not that big, despite the fact that it represents the vast majority of the compute available on the system. It's something like less than 10% of the overall die area of an H100 is going to be consumed by doing the matmulls. Almost everything else is the silicon required to basically keep those matmulls fed and move data around at all times. If you could make that less, you might be able to make the chips faster, although again, you're going to run into power and heat limitations relatively quickly anyways. There's a bunch of other things in an H100 that I'm not going to talk about that much right now, unless you want me to, in which case raise your hand and ask a question. So there are additional bits of circuitry near the HBM, like the tensor memory accelerator, that enable you to do more efficient things like striding and maybe even doing certain amounts of computation on the wire to the chip. So that way you don't necessarily have to come all the way down the memory hierarchy. We have, these two things I'll sort of lump together. The H100 also gives you new ways to coordinate the movement of data around the chip. So, for example, I can now have distributed shared memory, which means that between a bunch of different SMs that are kind of near each other on the chip, I can now pass data between them sort of directly without having to go all the way up to HBM and back down again, which is what you used to have to do. And so, again, I view this as a case of basically NVIDIA's looking to squeeze however much performance they can out of it. And so a lot of the nice primitives that they used to give you that were kind of, wrapped up to be friendly for the programmer, they're kind of unwrapping these things and saying, actually, no, we're going to expose the full kind of physics to you, and it's your job to use it as effectively as possible. Does that kind of make sense as an overall framework? Okay. Yes?
What percent of the work was done by the tensor cores again?
What percent of the work?
Yeah.
So if you're running without tensor cores, you're going to get no more than, like, I don't remember the exact number, 80 to 100 teraflops, I think. And so if you're running with tensor cores and FP8, you can potentially get up to like a couple thousand teraflops. And so I think the number Chris has told me is 30x. I think this probably depends on some assumptions in terms of, like, for example, if you're running in low precision, you're going to get more out of the tensor cores, relatively speaking, whereas if you're running in like very high precision, you're basically not going to get that much more than if you're using registers directly. But I think 30x it's a good kind of approximation for what the difference is going to be between these things. This is higher than it used to be. So and it really varies per chip as well. So on an A100 the difference was more going to be like, I don't know, 5 to 10x. Like it wasn't going to be 30x. On a 4090 it's actually probably even less than that. I really enjoy running on 4090s. I think 4090s are great chips. They're such good value and they're like remarkably fast. They also have a really nice memory hierarchy. I'll actually, on the memory slide that I'll talk about in a second, I'm going to show you I'll mention some things about a 4090 that are just very cool, because 4090 is actually more advanced than an H100 in a bunch of ways that I think people don't appreciate. Okay, so let's build some intuition about what's going on. So yeah, the system has 132 SMs that are running in parallel. You have about 1,000 teraflops, roughly speaking, of 16-bit precision performance. You have 3.3 terabytes per second of bandwidth to the HBM. So this is a ton of bandwidth that, this is an amount of bandwidth that I think would have been shocking 10 years ago that we'd be able to achieve. One interesting side story, maybe because I'm just full of tangents today, I guess, is that HBM actually kind of came out of AMD's work. So Nvidia was not the original player that spearheaded HBM. It was AMD, and AMD was basically looking at the scaling of gaming GPUs, and they thought that they were going to run into memory bandwidth limitations relatively quickly on them. And it turned out that wasn't actually true. So they worked with SK Hynix to develop HBM. That turned out not to actually really be all that true, and that gaming GPUs ended up not really getting bottlenecked by bandwidth in the same way. And so AMD actually abandoned HBM and went back to the regular graphics DRAM for their GPUs to save money. But HBM stuck around, and then people realized, in these high performance computing applications like AI, it's actually really valuable to have all this bandwidth. And so Nvidia kind of picked it up and has become one of the larger customers of HBM since then. So I actually ran some micro benchmarks on a Cloud H100 2 nights ago and putting this together. So I haven't been able to find super good numbers on this otherwise, but I'm getting about 12 terabytes per second from L2. This is a number I actually don't necessarily believe, and I think it may be too high. I've seen other numbers that are more in the range of 4 to 5 terabytes per second online. So I'm not going to give you a strong assertion of that one being correct, because I think the benchmark that I was using, I think might be inaccurate on it. The benchmark that I do believe is the 33 terabytes per second from L1. So in other words, if you're sitting like on the SM, you just have an unbelievable amount of bandwidth. This is actually still not as much as you get if you're going from the registers, which is harder to evaluate directly. If you're going from, if you really want to get the full compute, you really want to be sitting in the register file, not even in shared memory. But if you're in L1 or shared memory, you can get, another order of magnitude beyond what you're getting from HBM. And so again, this is me sort of like this is exactly what flash attention is doing. Is it's basically saying we want to sit as long as we can in L1 and shared memory and access that 33 terabytes per second when we're doing memory bandwidth intensive stuff, and that's exactly the right thing to do. This is what an actual roofline looks like overall for an H100. Raise your hand if you do know what a roofline plot is. Okay, most of you don't. Great. Then I'm going to tell you what a roofline plot is. So when we're talking about compute and memory, there's an important attribute called the arithmetic intensity. So what the arithmetic intensity basically means is how many bytes of memory do we have to move back and forth per compute operation that we're doing. It's a little bit fuzzy because, what is a compute operation, right? These days we count fuse, multiply, add as 2, even though we should probably count as 1. I don't really know, but as a sort of a general vibe, we have, there's some notion of a compute operation that takes some fixed 1 or 2 cycles to do, and then we have moving memory back and forth between the higher levels like HBM and the actual compute of the chip. And it's worth noting you could come up with different roof lines for different levels of the memory hierarchy. Right now I'm talking about the very highest level, that is to say from HBM down to the rest of the chip. So then what we're going to do is we're going to basically plot, we have a log scale, so here we're at an arithmetic intensity of 1, here we're at 10,000. So we're doing 10,000 compute operations per byte of memory that we move. On the y-axis, we're going to basically plot how much compute from the chip can we realize. So if our arithmetic intensity is very low, we're not able to use all of the compute available on the chip because we're basically just waiting for the memory to get to where it needs to go and the chip is stalled waiting for it. If our arithmetic intensity becomes sufficiently high, then we become bottlenecked by the compute of the chip. We're actually using all of the compute available on the chip. And so now we're getting, this is what we want. We want to be getting good utilizations. So the roofline plot basically tells you something about, what kind of a workload do you need to give the chip in order to get a lot of performance out of it. Does that make sense? Okay, great. So, and also before this, I said I was going to give numbers on the 4090. Just for fun, 4090 actually gets you 45 terabytes per second from L1. So it actually is much faster low-level memory. You also get 72 megabytes of L2 cache instead of 50 megabytes like an H100 does. So even though the H100 has better tensor cores and things like that, in terms of the actual memory movement, 4090s are phenomenal. They're really well designed for this. ADA is a great architecture. So, okay. In terms of a little bit of a warm-up, we're actually going to do a little exercise with a roofline, just because I think for fun to give you some intuition about how you need to run a workload on an H100 to actually get compute out of it. We're going to assume we're doing a 16-bit square matrix multiply. So n by n times n by n equals n by n. So the first question I have is, that was the answer. You didn't see that. If you didn't see that, you're allowed to ask this. How much compute is involved? How many flops do I need to do an n by n matrix multiply? O of n cubed is exactly right, and I will be a little bit more specific and say it's approximately 2n cubed. The approximate is that there's a -1 that you need on one of the dimensions, but it doesn't really matter when n is large. So it's basically 2n cubed. And where that 2 is coming from is it's coming from the fact we have to do both a multiply and an add when we're computing the dot product. We have to multiply two things and then add the result onto an accumulator.
FMA doesn't count as one flop?
No, it doesn't. For whatever reason, it is called 2 flops still by the industry. I think that this is stupid, and I think this is marketing by Nvidia, so they can say, look at how many teraflops we have. It's so many. Nobody wants to redesign it to be a lower thing and make their customers sad, because you would think that this is the kind of thing where everyone normalizes and understands that this is a new standard, but actually so many of these customers are pretty dumb enterprise customers that they actually just care about seeing the number go up. And so if you tell them the number went down, they will not buy as many of the chips compared to the supplier who said that the number continued to go up. So even if it's, anyway, this is why we're stuck in a slightly dumb counting scheme. How much memory does it take? There's another question.
n squared?
So it's O of n squared, that's right. So basically the way to think about this is I'm going to have 3 n by n matrices, right? The A, B, and then the output C. And each one has n squared elements, but we also are using 16-bit things, so that's 2 bytes per. So we actually have 6 n squared memory consumption overall. So that means that our arithmetic intensity is, someone finish this? Compute over memory? Right, so exactly, so it's n over 3. So we just divide the 2. So if this is what our arithmetic intensity is for a square matrix multiply, and we see that we only can sort of hit the roof line around, I think this is around 300 is the arithmetic intensity that you need. How big of a matrix multiply do I need to run to have any shot of doing this? So, yeah, 900, about 1,000, right? So in short, if you're running matrix multiplies that are smaller than 1,000 by 1,000, you basically can't hit the full compute of available on an H100. Like that is the level of density that we need in order to do this. Does that all make sense? So all this is to say that, if your model of the world is like, oh, I want to like build these like really efficient, small architectures that have like little tiny chunks and things like that, you're screwed. Like the hardware is not designed for that. There are other kinds of hardware that might be able to do that. And you could imagine redesigning hardware to be friendlier to that. But if you actually want to get the most out of an H100, you need to be running some pretty damn big matrix multiplies in order to have any decent utilization out of it. So I think this is something relevant. This is at least a concrete conclusion from this that may impact how you think about AI work, that a big part of what drives our algorithmic decisions is going to be what runs efficiently on the hardware. And even if there was some architecture that was a bit more efficient at an arithmetic intensity of 50, the reality is it probably wouldn't win because it's only going to get a little bit of value out of it's wasting most of its compute, and it would have to be 6x more efficient in order to justify that. All right, I think I've beaten this point home. So before we go a little bit further and talk about how exactly tensor cores work, I want to reframe one little thing for you in terms of how you probably think about computing when you are, or the difference between how hardware people think about computing versus how software people think about computing. Software people, broadly speaking, who are used to running on CPUs, think about computing from the perspective of how many operations you have to do, and that logic is kind of the expensive thing. And yes, we have to move memory around in order to make that logic work, but like logic is my limiting factor. I need to make sure I'm running the fewest number of sequential operations. That's kind of my overall incentive. I'm counting the instructions that I'm running, and that's going to give me a pretty good proxy for how long my program takes to execute. This is fairly inaccurate for understanding what's going on at the hardware world. In hardware, you will be surprised to find that logic is actually relatively cheap, and memory and data movement is like the problem. And to give us something of an illustration for what's going on and why this is the case, I have here a cross-section of the Intel 4 process. I would have found the TSMC one if I could have, but Intel makes this more easily available. So this is what an Intel 4 chip actually looks like if you slice it along the wafer and sort of peer into all the layers of it. And so what's actually going on here? So at the very bottom down here, these are the actual transistors. They're very small, as you can see. These, I believe you're actually seeing something of the fins as well, so these are going to be FinFETs that are so a particular kind of, they're not planar transistors, like they have this 3-dimensional structure to them that you can kind of see here. And then above it, you have all of these different metal layers. And the metal layers are much, much smaller at the bottom, and they get much, much larger at the top. And so the way you should kind of think about how the rat's nest of a chip works is that these very small metal layers at the bottom are extremely fast, and they're meant to sort of be used for local stuff, right? That if you're connecting a transistor to a transistor that's 6 transistors away, you're going to run on M0 or M1 if you can. And then these higher up layers are used for kind of longer distance communication on the chip. They're also used for things like power delivery. So for example, a bunch of these top metal layers are almost certainly being used as power rails to deliver power down via vias to the lower layers of the chip. These layers, I should say, are connected. You can see some of these vias here of how they get connected from adjacent layers. We're not going to talk too much about how vias and whatnot work, but in some ways saying that a chip has 86 billion transistors is actually a tremendous understatement of the complexity of the chip. The 86 billion transistors, that's just this bottom layer. Then you have everything on top of it that connects it together in terms of all of the complicated polygons that do it, and then all of the complicated work, which we'll talk a little bit about as well, that is necessary to actually make the thing. What you are manufacturing will not necessarily look like this, or the mass that you're creating will not necessarily look like this either. They will look quite different in order to get this onto the actual chip. So why am I showing you this before going into details on how systolics work? Well, the overall power consumption of a chip is basically driven by the following terms. You have the capacitance of the chip, C. So this is basically how much charge different parts of the chip are able to hold. You have the voltage of the chip squared. The voltage is going to define both how much charge gets moved each time and over what distance, right? And so that's why there's a squaring factor to the power consumption. You have the frequency of the chip. The faster you run it, linearly speaking, the more power it uses. Then you have this factor alpha, which we're not going to worry about too much right now. This basically says what fraction of the chip is flipping every single cycle. So if alpha is really high and you're flipping the whole chip every cycle, you use a lot more power compared to if most of the chip is static and not going anywhere. This is actually not including things like leakage current, which are also fairly important in modern chips, but we're going to ignore that for the moment. We're not going to worry too much about it. So, okay, just a quick show of hands. Who here knows what CMOS is? Okay, a couple of folks a little bit. So CMOS stands for complementary metal oxide semiconductor. This is kind of what I put this here just to be able to have a chance to talk a little bit about what CMOS is. So the way that these circuits work at the lowest level, right, is that you're moving little bits of charge around to represent ones and zeros. But there's different ways that you could do this. So for example, one thing that I could have done instead of this design is I could have said, actually, I'm going to have kind of a tie-up resistor here, like just a resistor between these things, and I'll be constantly dumping a little bit of current down up to there, and that way I don't need any more transistors to do this. So the benefit of that kind of a design would be that we don't consume any power in the off state, but we continuously consume power in the on state is the downside of it. So the way that circuits work instead is we basically have these two different channels, one of which is a p-type and the other which is n-type. And so essentially what will happen is when the signal A comes in, it will enable one of these transistors and it will disable the other one, right? So in the case that it's this is actually a NOT gate. So in the case that it's a 1, it's going to connect the opposite rail to ground and disconnect the other one from the voltage source. And in the case that it's a 0, it's going to be reversed. And so what essentially is happening, the way to sort of think about this is that every time I flip the thing back and forth, I take a little unit of charge from the top rail and I bring it down to the bottom, right? Every time that I go back and forth on it, like the charge comes first to the top by increasing this one, and then I close that one and I open the other valve at the bottom, and the charge sinks down into the ground. Does that make sense for a moment? And so this is the capacitance that I'm talking about. The capacitance is that little amount of charge times the voltage, or the capacitance of the voltage is the amount of charge that is being shifted every time I do this. So the more charge I have to shift, the more power I'm using. And all of this is a fairly long-winded way of saying that when I'm using these really long wires that are really big to transfer data over long distances, I have a lot of capacitance in those wires, and in order to drive them quickly, I need to drive a lot of charge into them and cycle them on and off. So I don't really want to do this. Like this is the most power-intensive thing to do. I would much rather be cycling these tiny wires at the bottom very quickly that don't have that much capacitance, and those are the ones that I want to be doing. So in other words, when I'm running on these sort of, this is like a little bit of a first approximation. When I'm running on these copper wires, the power consumption of sending a signal is going to be roughly proportional to the distance that I send that signal, because as the length of that wire gets longer, I have to drive more charge into it. Does that kind of make sense? I know that was a lot I just dumped on you all at once, but I hope you get some kind of a picture of what's going on in the sort of lower levels of the chip based on this. Any questions? Okay, please do ask, because I know that's a lot. Don't be afraid to ask. Yeah, so all this is again a very long-winded way of saying that I really want to keep my data as local as possible and do really short steps of communication, have transistors that are as close to each other as possible. And if I have to have a model of the world where I have to go get data from way over here on the chip and bring it back and forth all the time, right? That's how I'm going to use tons of power. That's how I'm going to burn up my chip, and I'm going to be throttled on heat dissipation, which would make me very sad. So we don't want to do that. Enter the systolic array, which is how modern matrix multiplies are actually done in hardware. Systolic array is a very, very clever design that enables you to put a ton of logic together without having to move data very long distances. That's kind of the reason for this to exist. And so the basic idea is I'm going to have an n by n, in this case we have 3 by 3, grid of these PEs, or processing elements. Each PE is responsible for doing a single dumb thing over and over again. It does, in this case, like a multiply add. That's what's going to run for it. And so what's essentially going to happen is that as an input comes in, the two inputs like A and B, it's going to do a, multiply them together, accumulate to some additional, to some sum, and then pass the result down, right? And this process will be repeated over and over and over again, such that the overall results of the matrix multiply will come out of the bottom of the overall systolic. But again, this can be done really densely on chip because there's no long wires between any of this, right? I don't have to have any direct connection between like this PE and the one at the top left. It's all just passed cycle by cycle through. So the end result of this is that if I want to do, let's say, I'll take what the Google TPU v1 had, I believe, a 256 by 256 systolic on it. So what that basically meant was that it could do a 256 by 256 by 256 square matrix multiply in just 256 cycles, which is a quarter of a microsecond or something like that, or can be less than that. So that's pretty damn fast to do a whole lot of cycles, because it's running, in this case, 65,000 of them in parallel every single cycle. Does that kind of make sense? I don't know I'm not sure I explained that particularly well, but hopefully the overall idea of it. I think this is the kind of thing I'll say as well, where like it's sort of hard to just like look at a systolic array and like see what's happening. But if you like basically go write it out and like do it, you will see it's like very natural what's going on of like, oh, these things go there, then I have to just add this and pass it down. One of the things that will also emerge, for example, quite naturally, you'll see how there are these zeros here, and they're the same at the top right as well, these zeros in the pipeline that are feeding in. The reason for this is that I have to actually create these shifts so that the result from the top left corner can get kind of down to here by the right time, right? Otherwise, if I feed them all in at the same time, then I'm going to have a misalignment of the data that's flowing through. So I need to wait to put in the bottom stuff until the stuff from the top kind of arrives there and I get that out. But you end up with this like slightly weird thing where the data feeding in kind of looks more like a parallelogram than a rectangle. Like it's a little bit wonky, and then you get it out in that form as well. So in order to really keep these systolics fed at all times, there's a bunch of additional circuitry that you need to do to kind of make sure that you're waiting to put each piece of data in at the right time, and then you can start the next matrix multiply before you even finish the first one. Okay, so that hopefully gives you some sense of what's going on there. I talked a little bit earlier about numerical precision. This is just a diagram that tells you a little bit more about exactly what's going on here. So it's actually a fairly old diagram. This is coming from 2014 on a 45 nanometer node. So the actual results today are much better than the results that you would see on this, but I can't find good results for what actually it looks like on a 4 nanometer process node. So the best I can do for you at the moment. One of the things I just want you to notice is that indeed, like the energy cost of going all the way up to DRAM or even like a relatively large SRAM chunk is vastly higher than the energy required to do a small like 8-bit fused integer multiply add or something like that. It's like orders of magnitude difference. These differences are even more remarkable in CPUs than they are in GPUs. One result that I really just like stuck with me. So let's say in a like 2014 era CPU, because that's also where these numbers came from, you do a like int32 add instruction. So if you look at where the power goes, the overall operation takes on this particular CPU something like 70 picojoules to do, and this is already just sitting in registers on the CPU. So we're not doing anything, any complicated DRAM load, like just in registers running an int32 add instruction. Overall instruction 70 picojoules. The actual int32 add is only half a picojoule. So 99.3% of the energy is going to other things, right? To the control flags, the register file accesses, pipelining and prediction and all these other kinds of processes that go into how this, the micro instruction decoding, all of these details of how CPUs work. And I should say, this is not to say that CPU designers are dumb. These things are necessary in order to build really, really fast sequential pipelines and predict what's going to happen next, the same way that speculative decoding is useful in transformers too. It's not that CPU designers are dumb, but it's that they're designing for something where they just care about sequential execution as fast as possible. They're not designing for power consumption. And as a result, you end up spending like the vast majority of your energy on things that are not that, even inside the CPU, let alone doing, an L3 cache bis and then going up to a DRAM access or something like that, which would be much, much more expensive. So yeah, I think that gives you a sense of kind of what the overall orders of magnitude here are and why we care so much about being as low and as close to the silicon as you can be. I think the next slide is networking. Yeah, so I'm going to talk very briefly about networking. I'm not really going to do it its full justice because networking is actually a really important, complicated topic right now. This is a quick diagram of an 8-byte Bettis network, which is a certain kind of something called a Kloss network, which is the actual topology that's used inside the NV-link bridges between a bunch of different H100 chips. So that's what, this is actually not what it looks like because this is a simplification of it. True Kloss networks are going to have a kind of a larger cross bridge at each layer, but I can't find good diagrams of that, so I'm going with the easy one that's understandable. This basically gives you some way to drive any permutation between some set of inputs to some other set of, some set of outputs by just switching essentially the switches inside each one. That's what's going on here. So why is networking so important? Well, we know that scale is an important thing in terms of making sure that our LLMs train quickly and run quickly and all this. We need to have thousands of chips connected. But connecting thousands of chips with lots of bandwidth is really, really quite hard, right? Everything that we were doing before was on the chip and we could sort of be running it at these layers. But all of a sudden, now you're telling me I have to go out to some actual physical wire or fiber optic that's going to run a real physical distance compared to nanometers, right? This is a pain in the ass. So, basically, the thing that mostly saves this is that you can build very thin wires when you're running on PCBs between these things and linking them together that way, and also optical switches. And optical switches, I think, are both the present in the sense that Google's TPUs are entirely connected by this complicated optical torus structure, and it's also the future. I think Nvidia is clearly going to move to more and more optical connections. We're even going to see optical stuff exist on chips, I think, in the next couple of years because the bandwidth advantages are just so extreme. But yeah, networking is a really important, complicated problem. There's an interesting article from SemiAnalysis, Dylan Patel, about how Nvidia is one of the companies that has, one of the few companies that has more than $1 billion of revenue associated with AI chips. The other one, which is sort of surprising, is Broadcom. And that's because Broadcom sells the switches to connect all of the chips together. My overall philosophy for how I think about networking is I don't want to do it unless I absolutely have to. Because it's just a pain, right? Once you have to start and go and coordinating multiple GPUs and linking them together and deciding, am I going to do tensor parallelism or model parallelism, everything gets really complicated, and the hardware gets complicated too at that point. The memory controllers are generally the more complicated parts of a chip, actually. So you really want to avoid going off of the silicon for as long as you can, and you want to squeeze as much performance as you can out of the silicon that you have. But eventually, if you want to go train something that's really at GPT-4 scale, you have no choice but to scale up to 10,000 H100s, and then excuse me. At that point, the networking all of a sudden becomes kind of the key problem, to the point that if you read the TPU v4 paper that Google published, you may be surprised to find that very little of it actually talks about the TPU v4. Almost all of it talks about the networking between them and the complicated optical torus, 3D torus structure that Google builds between them, which they seem to think is the right solution. And I would say the evidence right now is probably that it is the right solution. I think they're getting great performance out of it. That's a little bit on the networking side of things. It's a super complicated topic that also is fairly different from what the rest of the chip kind of industry looks like, right? These optical switches are very different manufacturing techniques and different processes and properties and different physics than working in silicon with electrons. But I think it's also kind of, if I were to go at sort of a more philosophical level, I think it's right. You want to be using bosons that can stack on top of each other to transmit information, right? So light, it makes sense to use light to transmit information. You're getting great frequencies out of it, in a terahertz regime, and you're able to stack many different frequencies on top of each other and do wavelength multiplexing on it. So that's why you can, on some thin waveguide, put so many gigabits or terabits per second on it. The flip side of this, though, is that bosons, because they stack on top of it, they don't interact, they seem to me like not the right solution for actually running compute. There are some people that are interested in doing things like nonlinear optics to get you can get photons to interact in certain ways in the presence of strong fields, and then maybe that's the way that in the long-term computing will run, and we'll be using photons to do the computing too. But at the moment, the nonlinear optics seems like it's a pretty far ways out. And at the, using fermions that actually interact with each other to do the compute where you need an interaction to happen seems kind of right to me. So I think there is a a reason, sort of a good fundamental physics reason to think that the networking stack, the memory movement stack, should actually look very different from the compute stack. Okay, so with that, I'm going to move on to how chips are designed and manufactured. This is going to be an extremely very fast overview of what is a $400 billion industry. But I think it is worth at least a brief discussion because it is actually quite interesting and quite important. I'm going to start with the design side of things. So how does it work? The first step, which is actually optional, is probably not used most of the time, would be high-level synthesis. You might say, I want to write my chip in a higher language and then compile it down into the actual circuit that I want. Sometimes this makes sense, and there are some people that claim good results with high-level synthesis in certain limited domains. But on the whole, I would say high-level synthesis is not used very much in practice. It's too risky if you get stuff wrong, and it's also something where an actual experienced chip designer is going to probably do a better job of writing the RTL than the modern compilers will. The compilers aren't smart enough at the moment to beat real engineers who know what's going on. As we'll also see, writing the chip is actually the least difficult part of the overall process. Everything that comes after is kind of the hard part. So logic design, RTL, that's writing something like Verilog to compute, say, I want this wire to be attached in this place to this sort of thing. This will be a register of, 32 bits or something like that, whatever. Next step that's going to happen would be something like functional verification. So we're basically going to run against some set of tests that we have written in C or some other language and say, does this chip, if we simulate the RTL that we've written, does it do what we want to do? And at a high level, the one good sort of thing to keep in the back of your mind is that in chip design, approximately 1/3 of the overall time and effort and cost is designing the chip. 2/3 is the testing and verification. So most chip designers actually spend their time checking the work, not actually doing the work. And it's basically because if you get it wrong, it costs you months to go fix the problems, do another tape out, design the new mask set, get it put into production. It's $100 million of direct costs and probably many hundred millions more of indirect costs in terms of sales that you weren't making and being delayed relative to the industry. So you really put a lot of work into making sure you did it correctly. The next kind of thing that will happen will be synthesis and optimization of it. So we're basically going to take all of the wires and registers and whatnot and convert them into an actual logic gate network of, hey, we have these kinds of standard cells from the fab. So TSMC will say, hey, this is a 2-input NAND gate, right? And this is kind of what that's one of the things I'm giving you to play with is a 2-input NAND gate. And then these compilers will basically go and say, okay, I have this kind of combinational logic I want to produce. What's the best set of NANDs and NANDs and whatever else that the fab has given me to accomplish this goal? This is a surprisingly hard problem. It's not just an intractable NP hard problem. It's like a doubly intractable P-sharp hard problem. Despite that, the compilers work pretty well in practice and you get pretty good results. They've also gotten a lot better recently. I don't know how far we are off of any sort of theoretical optimal, but my guess is that the compilers are not by no means optimal, but they're pretty good. We're getting pretty good net lists out of them. The next overall step, and each of these things actually consists of 10 different sub-processes of them of floor planning and clock tree synthesis, and then place and route preliminary, and then you go and mess with the clock tree and the net list a little bit more. You go back, there's a bunch of back and forth of optimization of these things. But the physical design is to say, okay, we have this net list. Let's actually go lay it out onto the chip. Let's go and say, okay, these things we think should be over here. These wires need to be in these particular places to connect them, so we have to make sure that the routing of all the wires doesn't interfere with each other. There's going to be a bunch of different constraints and tolerances we have to hold as well between them. So the fab will give you a bunch of design rules that will be of the form of no wires can be closer than this amount, or if I have a T-junction, there's to be a separation of an even larger amount between them. A bunch of particular geometric rules that they need in order to ensure that their process goes smoothly and that you don't end up with bad results. So part of the responsibility of the physical design is to make sure that you do all these things. Then eventually we will have verification and analysis. So this is the part where we're going to go and again do more simulations on everything we just produced and try to make sure that it actually matches everything that we did before. I would like to say that I think it's astonishing that this stuff actually does end up working, because most code that's more than 1,000 lines has bugs in it of some kind, and the amount of compilers and design rules and coordination between different companies that is required in order to make sure that all of this happens is actually just enormous. And I would be surprised if Synopsys DC and IC are not full of bugs in them that get caught at various stages and I mean, they're very rare, I'm sure, but it's just impossible when you're writing, hundreds of millions of lines of code for it to all be perfect. The verification analysis, there'll be a bunch of other things that you need to do beyond making sure that the circuit, is the same netlist and is the same logic that you wanted from before. There will be things that you need to do, like, for example, check different RC corners. So in other words, there's going to be some variance from the fab in terms of what the transistors will actually be, right? You would hope that everything is just, atomically identical and physics gives you the exact same behavior, but these things are actually surprisingly organic when you get down to the lowest layers. So, what happens if your transistor is 10% faster, or 10% slower than you thought it was going to be? Does everything break? So you need to sort of go run analyses on, if I get a little bit unlucky, do I still meet my parameters, right? And that's going to influence the overall yields that you're going to get out of the manufacturing process. Finally, we'll do a tape out, which basically means we're going to take the whole design and we're going to actually write it out onto the, it comes from in the olden days when you had an actual physical tape that you would send to the fab that had the whole design on it. These days it's not that, but the actual particular sets of polygons that the fab needs, and you're basically going to do that and send it off to them, and they're going to go out and do the manufacturing. So I have, again, this is the diagram from before. So you can see we have all these different layers of, the tape out is going to include all of the geometries at every single stage of it. And this is, hundreds of terabytes of data at the very least to incorporate all of the different rectangles and all the complexity of the masks. It's like a ridiculous problem actually to go and not just store it, but also optimize it, as we'll see. It's not, even if you know what the shape of the wires that you want is, it's still a hard problem even beyond that to just figure out what the mask should be in order to print that, given all the diffraction of light and other things. So this is, I just did want to show you, this is sort of what a FinFET looks like. This is actually a single FinFET. These days, usually you'll have multiple different things that, like multiple different fins that run through it to give you more overall, what's the word I'm looking for? More current, basically. Like you can drive a larger load if you have multiple wires. But essentially, the reason this is going on, so transistors used to be planar. Used to basically have a flat level, and then just you would make something on top. You'd put the gate on top of it. The basic problem with this, though, was that as things got really small, you basically started to find that the gate didn't have enough actual kind of control over the flow of current from the electric field it was producing was sort of not strong enough to really do this. So we went into 3D and we said, okay, we're going to actually wrap the gate around the wire between the source and the drain, and that way we're going to make sure it has 3 sides of contact. It's going to have even stronger control. And as we're going to smaller and smaller process nodes continually, like Samsung's newest, I think 2 or 3 nanometer process, I believe, is running something called a gate all around, which basically means that we actually we lift this thing up, and now the gate runs around all 4 sides of it, so that we have the most amount of control over it. This is all, a sort of a nightmare to manufacture. I have no idea how they do it, really. But just to give you a sense of the kind of geometry that need to be produced at the small scales. And so in general, the transistor layer is really the hard part of it. When you go to the metal layers, I'm not going to say the metal layers are easy. The low metal layers are also still pretty hard, but as you go to higher layers, the pitches get large enough that we kind of know what we're doing, and you're not likely to get yield failures in really high metal layers, I don't think. So what are the actual processes that go into it? So for starters, to understand what's going on, we have a wafer. These days, the wafer is 300 millimeters in diameter, so it's about 12 inches, the size of a dinner plate. And we're going to basically tile as many of the chip that we can onto that dinner plate. And then we're eventually going to dice it up, which we'll talk about in a second. So these are the kinds of things that this is the overall structure of it. So that way we're making a bunch of them at once, and it's sold per wafer. So if you do out the math, I believe that if 300 millimeters squared times pi over 4 divided by the maximum reticle size, which is 830 square millimeters, or actually let's use the size of the which is 814 square millimeters, you get something like 80 to 90 chips per. I think you're probably getting more like 80 chips on it. So TSMC is going to sell it per wafer. So, and they're not going to control for yield. So if some of the chips don't work, that's on you, and they're doing the best they can. But you're assuming that in basically the pricing of the wafer that you're buying. The wafers are quite expensive. These days, a wafer for a foreign process, something like $18,000. Although then again, it has 86 dies on it, or 80 dies, which is also quite a lot. So what are the processes that you need to do? Oh, I meant to make that go by bullet. Whatever, it's fine. So the most important process, which is the only one I'm going to really talk a little bit in detail about, is something called photolithography. This is the process by which we actually put the detailed designs that we want onto the chip. So in other words, how are we going to say, hey, this needs to be in this particular place, right? We have information kind of from the tape out, like how does that information come onto the chip? Photolithography is generally the process by which this happens. And I'll give you a little bit more detail on that in a moment. There's a bunch of other processes though that I want to talk through in at least brief discussion. So we have, for example, ion implantation and diffusion. These are generally processes used for doping the semiconductor. So if I have the overall silicon wafer and I want to make part of it N-type or P-type so that I can make my transistor, I'm generally going to do this these days with ion implementation. You used to do it more with diffusion, where you'd basically heat up the wafer in an environment where a gaseous version of it is present, and it would just sort of kind of diffuse into it. It turns out this is not quite as specific, and it's too isotropic in terms of how it diffuses into it, so you end up with less clear boundaries. So these days, the more common approach is ion implementation. You basically have a particle accelerator, you take ions, you run them through the particle accelerator, you slam them at the wafer, and you get very clean, directional implantation of the ions that you want, and that way you can create a very precise doping. Processes like etching are very important. So in addition to being able to put things onto the chip, we need to be able to take them off it. There will also be, this is another case where we used to use something called a wet etch, where you would have a chemical that would, some sort of hydrochloric acid or something like that would just etch away physically at it. The problem with this is that, again, this is an isotropic thing. So you can get things like undercuts where as it starts etching, it starts to go out laterally sideways underneath the resist, as you'll see what I'm talking about in a second. And this can, again, if you have small features, that can destroy your features. So these days, more etching is done with something called plasma etching, where you can basically have a plasma, it's directional, and the plasma chips off little parts of it. And this can actually be done in a very controlled way. I mean, each individual part of the stack is itself probably $1 billion industry that's associated with companies that specialize in just making plasma etch or just doing ion implementation. We have deposition and metallization. These are, we want to set new layers down on it. Metallization is specifically for putting down the metal layers of it. We have things like chemical and mechanical planarization. So essentially what happens is as you're building up the chip layer by layer, you will gradually, just by sheer chance, create some sort of ruggedness on the surface of it. It won't be as perfectly flat anymore as it used to be. And so what the CMP is let's take a moment and flatten everything out so that our new processes are working on top of a flat base and that things don't get too out of hand. Dicing is one of the processes at the end where we basically take this and actually slice up the wafer so that we can take the individual chips from the wafer. Then we have packaging processes, which are these days also incredibly complicated. And there are things like advanced packaging and CoWoS, which we'll talk a little bit more about later. CoWoS is chip on wafer on substrate. So these are the techniques by which you can integrate a bunch of different things like HBM and chiplets and other things onto the same overall package. Then there's, of course, testing. And you have to check, once you've done all these things, that you did them right so that you don't send out dysfunctional chips. And so also a lot of the work involved in building these chips is going to be to design into the chip lots of sort of little testing hooks that you can say, hey, is this part of the chip working correctly or not, right? And then that way, when you discover, okay, this part of the chip is, let's say this SM is not working right, Nvidia can disable that SM rather than throwing out the whole chip. I'll talk a little bit about photolithography. So here's an example of a starting process. So here's my wafer with some stuff on it, whatever. And the first thing I'm going to do photolithography is I'm going to deposit a photoresist. This is called the coat phase. So this pink layer I've just put down as a photoresist. This is a chemical that is going to be activated by some kind of light. This is actually a fairly complicated process when you get to really small wavelengths of light. The actual photoresists that are used are very complicated and completely trade secrets these days. So nobody knows exactly what the photoresist is that's being used on modern EUV processes. The way this is generally done is with something called a spin coat. Basically take the wafer, you spin it up really fast, and then you put a bit of photoresist in the center of it, and the inertia of it spinning kind of spreads it very evenly into a thin layer over the whole wafer. The next thing we'll do is we will expose it. So we'll put a mask, which I've outlined in white and black up there, and we'll shine down light of some kind, and that light will hit the photoresist in some places and not others. And that is, in turn, it will cause a chemical reaction that kind of imprints the information that we wanted onto the photoresist. The next thing that we will do, we will develop it. So now we're going to hit it with another chemical bath that's going to wash off the parts of it that have been exposed and not touch the parts that haven't been exposed. And then we will etch or something like that. So in this case, I'm imagining we're using our plasma etch, and we're going to go and hit it with the plasma, and this is going to to directionally do it. If we were using a wet etch, the undercut would sort of be along there. That would be the risk that we would run. And then finally, we will strip off the remainder of the photoresist, and now we've successfully, etched the chip in the areas that we wanted to etch. So I'm bringing this up for a couple of reasons. Part of it is that this is one of the most important rate-limiting steps in terms of our ability to make chips smaller. Like the ability to put the mask that we want onto it is kind of the hardest process right now. There's lots of other parts. I'm not trying to say that these other parts like etching and ion implantation aren't hard. They are actually quite complicated too. But at the moment, the ability to put really tiny patterns onto resists is actually the limiting factor. And it's also an important geopolitical thing. So raise your hand if you've heard of ASML before. Okay, many of you have, excellent. So ASML is a Dutch company. It is, I believe, the largest European tech company by market capitalization at the moment, which is in some ways more of a statement of the sad state of affairs of European industry than it is about tech, but nonetheless, anyway, it's a really amazing company. So what we were showing here is something called it's like the TwinScan NXT 2000. It's an EUV photolithography machine. So what it basically means is that this is the machine that is going to generate, collimate, and focus the EUV light on a mask, reflect that off it, put it onto the wafer, in order to imprint the patterns that we want on it. And I mean, I don't want to go spend too much time on this, but I do want to take a minute or two just kind of give you a sense of how insane this machine is. The mirrors in it, which are something called Bragg reflectors, they need to have many alternating layers of materials. So they do the reflection by diffraction, because the EUV does not reflect the ways you want it to. EUV is really hard to work with. So it's a 13 nanometer scale of light that we're running on. So very deep in not just the ultraviolet, but basically in X-ray territory. These Bragg reflectors are literally the smoothest objects in the world. Like NIST tried to make smoother objects with their silicon sphere for redefining the standard. It's not nearly as good. This is the smoothest stuff that there is. I think I remember that if it was scaled up to the size of the Earth, it's millimeters apart, the levels of flatness that we're achieving here. These are made by Carl Zeiss out in Germany, the lenses. The source for the EUV is actually made here in California by a company called Cymer. It's based in Santa Clara, I believe. They basically take tin droplets, they form them at 50,000 times per second, they hit them with a laser twice. It turns out you need two lasers in order to get this to work, and that generates a sufficiently high power UV source that you can make the rest of it work. I mean, other things that need to happen is, the wafer itself has to be scanned under this EUV source incredibly quickly and at sub-nanometer precision. So the wafer is being accelerated at 20 Gs around moving it, to scan the next part of it, and yet it still has to come within, fractions of a nanometer to the right place so that you're aligning each level of the mask with the levels under it. It's just alien technology. I don't understand how it can be done. So when the reason I bring this up is to say that when the Biden administration cuts off access of chips and these devices to China, which it has been doing, the Biden administration can do this basically because they use lots of American technology, and also, frankly, just America has enough say on the international stage to prevent the Netherlands from exporting these machines to China. Basically, the reason that this may be effective is that these machines require a truly global supply chain to make. The photoresists come from Japan, the mirrors from Germany, the lasers from the United States. What America is sort of telling China at the moment, and I make no commentary on the positives or negatives of the geopolitics, I'm simply explaining, I think, what I think is going on, is you have to go reinvent all of this, right? You can't just try to be ASML. That alone is a hard enough task, but you have to be ASML and Zeiss and Cymer and 10,000 other subcontractor suppliers that go into making these machines, each of which I should add costs $150 million. So this is kind of the most important choke point, in my view, of the overall global semiconductor supply chain. There are other choke points, like the United States does, for example, control most of the EDA software stack via Cadence and Synopsys. Siemens does a little bit of the metrology, but verification, but it's not as important. The US controls most of the EDA stack, but my read on that is it's probably not actually truly defensible, and that's the kind of thing where another country that really wanted to build their own EDA stack, they could do it. It probably wouldn't be quite as good, and it would take them some time and effort, but they'd put it together. EUV is the one particular technology that I think would actually be, a decade of work to go and try to rebuild the whole supply chain to do it. I'm sure China is trying, but it's just a hard task. This gives you some sense of other things that go into how you actually put these patterns down. So on the top, I have this is the mask that I'm desiring to produce. That's the shape that I want. So the first row is basically, let's pretend that I'm going to keep the mask as it is, and I'm only going to vary the illumination field. How well can I construct what I want? And the answer is like, okay, but like not that well. So what actually ends up happening is that you do something called inverse lithography, or ILT. And not only do you mess with the illumination field, but you also mess with the mask itself in terms of the what is on the thing that's being reflected onto it. And you're basically counting on the diffraction patterns to give you what you want, which they actually do, and then you get a much better rendition of what you're going for. So when you're doing the process of designing some low-level metal layer, like you're not only doing the taking the rectangles and trying to put them via some electron beam scanner onto the actual mask, you're also doing all of this inverse lithography to come up with something that looks crazy like this in order to get it to actually work at the lowest levels. What I have at the top is actually kind of the key equation for what's going on here. So CD is the critical dimension. This is sort of the smallest resolvable feature size. And this is equal to K1, which is kind of a quality factor, times then you have the wavelength of light that you're using. So in this case, EUV, we're using 13.5 nanometers. And the numerical aperture of the device is essentially, it's sort of a way of saying how big is the lens, but that's not like exactly the right way to think of it. Generally speaking, when you have a larger lens, you capture additional information coming off the diffraction patterns from the light source, and you can reconstruct it better, so your critical dimension goes down. Like that's why this matters. So basically, lambda is fixed by the light source. The numerical aperture right now is fixed at 0.33 by ASML. They're trying to do high NA, but it's not clear that it's going to be better compared to doing multi-patterning instead, where you use multiple different exposures. So basically, the main thing that we can play with right now is this K1, and that's why this inverse lithography and all this is so important, that actually, if you're able to vary the illumination field and the mask and other things, you can get better resolutions onto it. I should also ask that the hard part of all of this, of course, not doing it once or twice, but it's doing it millions of times at scale economically. And that's what makes this all just such an insane supply chain. Finally, in my last couple of minutes, I really managed to drag out these slides longer than 45 minutes. Excellent. I'll talk a little bit about economics of an H100. So if we look at the bill of materials of what Nvidia is paying, the actual logic die is probably running $200 to $300. My best guess is $230 based on the yields that they're getting, although I don't know, it may be a little bit more than that, but it's sort of the right ballpark, is $230 to $300. The HBM is a lot more. So these days, HBM is probably running something like $15 per gigabyte. It may come down, but at the moment, last I've checked, it seems like it's around there. So it's more like $1,200 to put together the memory stacks for it. And in some ways, I should say this also makes sense in that, yes, the logic die has 86 billion transistors, but the HBM should have at least 640 billion transistors, and probably more than that, since it has its own logic on it too. It's a bunch of different layers of DRAM that have basically been stacked, drilled, and then had vias created and plated between them. CoWoS is the one I'm having the most trouble getting good figures on. So CoWoS is the packaging that's used where you have the chips on top, and then a wafer, and then a substrate beneath it. So chip on wafer on substrate, CoWoS. This is the integration of the HBM and other parts of it too, chiplets in the future perhaps. We'll see what Nvidia does. The best figure I can find right now is 260, although Chris tells me that it's more, and because we're in a little bit of a supply chain crunch for it right now. CoWoS is actually the limiting factor in the production of H100s. That is the thing that's driving the overall shortages right now, is the fact that CoWoS supply just hasn't been built out enough. The logic and HBM are actually not the limiting factors in production at the moment. And then there's, of course, other things like the power supplies and PCBs and shipping and other things. And as best as I can tell, that's something like 1,500. This is with a lot of asterisks on it. The actual average sales price of an H100 is somewhere between $20,000 and $40,000. They listed $40,000. Most of them are probably sold for something more like $30,000. And if you're a really big customer like Meta, maybe you're getting them for more like $20,000. But in any case, Nvidia is probably driving something like an 80 to 90% margin in basically all cases for it. So the reason I bring this up is to say that if you want to figure out where the money in AI is going, when we say that GPT-4 costs $50 million to train or whatever, where do those $50 million go? Is it going to SK Hynix for the memory? Is it going to the power companies for the electricity for it? nope, the electricity is $500 a year. That's like actually a pretty irrelevant expenditure, as I said in the beginning. It's basically all going to Jensen Huang's profits. Like this is going straight to Nvidia's bank account. All of the inference costs that are associated with running the GPUs, they're Nvidia's profits. All of the training costs, aside from Google, which is its own story, they're Nvidia's profits. Like, and so this is a big story. Like, one of the reasons why there are so many gunning for Nvidia at the moment, Google with their own TPU stack, Microsoft's making their own hardware, Amazon's making their own hardware that doesn't seem all that good, Meta's making their own hardware, all the hyperscalers, so all the hyperscalers want their own stuff, a bunch of startups, GraphCore is not doing very well, there's Sambanova, there's others like Etch that's coming in. Like they all want to come here because the margins are so high and there's so much demand, and at the moment everybody wants to buy these chips. Intel has their gaudy stuff that actually looks like fairly good, surprisingly. So there's a bunch of details in there. But anyway, this is why I think there is a lot of alpha to be gotten on the hardware side. In terms of where things are going to go, I think we're going to continue to see growth of the amount of compute on these chips, especially via just larger fraction of the chip being taken up by these big systolics, and probably ways to reduce power consumption further, low voltages and whatnot. I think we're going to see continued increases in networking bandwidth. I think eventually we're going to see photonic interconnects on the chips to drive a lot more memory bandwidth. I think we're going to see continued development on the optical networking stack between the chips. And I think, unfortunately, the memory hierarchy is probably here to stay, and then we're going to have to get good at writing for these like fairly deep parallel memory hierarchies if we want to actually squeeze performance out of the chips. So I think with that, I'm at time. So I will stick around if anyone has any questions, and otherwise, thanks for your attention.